Hi folks, so in this video I want to talk about the domain and range of exponential functions, and we kind of mentioned this in the last video when we were talking about the graphs, but I just want to show that using tables here. Okay, so with the domain and for domain range, we'll make a table here. So again, the domain is the set of all x values that we can plug in. Excuse me, sorry, I had a little brain freeze there. So what x values can I plug in? Well, I think we can see I can easily, I'll start off with 0, and that's not so bad. Okay, 2 times 3 to the 0. 3 to 0 is just 1, so that's just 2. If I plug in 1, can I do 2 times 3 to the first power? Absolutely, that's just times 3. 2 times 3, which is 6. And I can keep going here. 2 times 3 is 3 squared and get to 18, and so on and so forth. So I think going forward, there's no problem at all here. I could plug in, heck, if I wanted to, I could plug in 10,000, and I'll say, okay, that's 2 times 3 to the 10,000th power, which is some big number, right? And we could do it. That number exists, and there's nothing wrong with that. Could I plug in negative numbers, though? I think so, because we know what negative exponents do and how they work. So if I have 2 times 3 to the negative first power, remember, that's just 2 times 1 over 3 to the first. So that's just 2/3. If you're unfamiliar again about how negative exponents work, another way we could do this is to just follow the pattern backwards. Remember, going forward, we're multiplying by 3, multiplying by 3. Going backwards, we would simply do the opposite, dividing by 3. Again, similar to a linear function, if going forward you add 2 plus 2 plus 2 plus 2, then going backwards you just subtract 2, subtract 2. And we can follow this same pattern. We'll divide by 3 again and get, let's see, 2/3 divided by 3, that would be 2 over 9. And then we get that. So I think there's actually nothing wrong with plugging in any positive number here or any negative number here. And so I think it's safe to say that the domain can be all real numbers. All real numbers. Again, if you want to say be fancy with it, you could use this notation. And that's saying that x can be any real number. If you're careful when I was doing my explanation here, you might have noticed I actually did leave something out. And I'm gonna actually that wasn't actually intentional, because I want to address that later. Okay. So let's talk about our range now. Again, the range is all the y values, all the outputs that could come out of our function, all the y values. So I think we can see going forward, again, this thing is going to get bigger and bigger and bigger, as we can see here. So there is no cap on the y values. So I'll say here, there's no maximum y value. I think that's pretty clear. But what about going backwards? So I'm going to kind of rewrite this table just on its side here. So just give me 1 second here. Okay, so what I've done is I've kind of created the table, but I'm starting off at 0, and I'm going from right to left in this case, just because it helps going backwards. So again, going from left to right in the x values, we know that it's going to just keep growing and growing, and it's not going to stop growing, really. Going backwards, though, it's getting smaller. So going backwards from 2, it will divide by 3 to get to 2/3. Divide by 3 again. Oops. Divide by 3. Get to 2 over 9. Divide by 3 again to get to 2 over 18. Okay. So we notice the denominators are getting larger, but the numerator of these fractions is staying the same. So that means that our overall fractions are getting smaller from right to left, which makes sense because it gets larger going from left to right. But the question is, how small does it get? I think you should pause the video here and just think about that question. If we keep dividing by 3, dividing by 3, dividing by 3, where are we going to end up? So I'm going to assume that you did that and you paused the video and thought about this. But if I were to keep going, I'll get 2 over 54, I believe. And we'll keep going and going and going. This number is going to get smaller and smaller and smaller, but there is actually a ceiling. Well, not a ceiling, rather, I guess a floor for how low it can go. Right? Where is that floor? Well, think about this. Is it ever going to get negative? Well, there's no way it can be negative, right? Because this number, that's positive. And dividing by 3, well, 3 itself is also positive. And if you take a positive number and divide by a positive number, you're still going to get a positive number. But think about this. As you keep going and going and going, this number is going to be smaller and smaller. So here's the question. If you're always going to be positive, but you're still going downward, what's the floor? That's kind of like your barrier from going negative. And that floor is 0, right? So what's going to happen is, and you'll see this if you keep going further and further and further, if we suppose we plug in negative 10 for x, then our y value is going to be 2 times, 3 to the negative 10. So that's really 2 divided by 3 to the 10th. And I'm going to pull out my calculator here. Okay, so I pulled out my calculator. Sorry about that. And I got 0.0000, so 4 zeros, 3387, and some more decimals, of course. Okay, so you can see that this number is very, very, very tiny. But again, it's still never going to hit 0 because you're still dividing it by a positive number. And so what we can say is that this graph is going to keep, again, going backwards. Can get lower and lower and lower, but we'll never hit 0. But we'll never reach 0. And so what we can say is that our y values, again, our y values have no maximum, but they do have a minimum, and that is 0, except they'll never hit 0. So that's why we could say the y values are going to be greater than 0, but not greater than or equal to 0. If we think about this graph of this is what you're going to see then. So again, it's got a domain of all real numbers, so we can go from left to right for as long as we want. But you're never going to, I should probably put this on the line here. You are never going to actually hit the x-axis there. And so what's going to happen is you're going to get ever so closer and closer. And if you zoom in, if you could always zoom in, assuming I could draw it better, there's always going to be a tiny, tiny bit of space between your graph, this one, and the x-axis. So this leads us to give the x-axis a special name. So I'm going to draw the x-axis in green here, actually. And we'll often draw it with a dotted line. In this case, the x-axis is an asymptote. And it's going to have this spelled funny, asymptote for the graph. What's our function? 2 times 3 to the x. Again, asymptote has a number of, it has really only one meaning, but as you get further in your math career, you'll see kind of more formal explanations. But put simply, an asymptote is a line or another graph, because there are nonlinear asymptotes, but it's a line that your graph gets closer and closer and closer and closer to. It can cross that line, but for our purposes right now, just like early algebra here, we're not going to really worry about that too much. Okay, so for us, we would call the x-axis an asymptote, because our graph gets gets closer and closer and closer and closer to it. And that's all. I do want to just add one more thing. This y being greater than 0, the range here, that's based on the fact that this graph has a positive y-intercept, right? It's got a positive y-intercept at 2. If our graph was, again, facing this way, like so, for example, I don't know, y equals -2 times, 5 to the x, then our domain would still be all real numbers, but our range would be y is less than 0. But for the same reason, right? Just going backward, it just stays negative, and it still gets smaller and smaller going this way. Okay. So hopefully that makes some sense. Hopefully we learned a little bit of new vocab with the asymptote, but hopefully we also see why, again, just based on what we know, right, about how multiplication and division work, why our graph can never actually reach 0. Alrighty, so thanks for watching, folks, and I'll see you in the next one.